Okay. So what follows? I will try and make this more intuitive by showing pictures. So let me give a few comments to what we've just derived. In all our derivations, we had these true densities. So the base classifier, we now know what it is. It's really easy to write down in terms of a formula, but this base classifier relies on the knowledge of the true density of the classes and also on the true prior probability of each class. And this is, of course, the weak spot. In reality, what we will do is we will substitute the true class density with various estimates of class densities. And the other comment is that, yes, this base classifier is the very best possible classifier that there is in the world, but best, unfortunately, does not mean perfect. So remember these data sets that I showed last time? Even if I did know the true density, I'm fantasizing this density now, let's say the black density. Actually, I generated it so I know that it was really two Gaussians. Even if I did know the true density here, it is just not possible to get perfect predictions. In other words, the expected loss here is going to be high. Here, on the other hand, in the bottom example, the expected risk or the expected loss is going to be lower. Okay, then I've been using these words, posterior probability and such. Let me give them again in more detail. So what we see here is Bayes' theorem, written in this case for class 1. And here we have the probability of class 1. This is the prior probability. This diagram is again in your public OneNote folder. This thing here is the density in feature space. You see that this is a marginal density. So we've integrated out class membership. We just ask how likely is it to get an observation in that region of feature space. Here we call it density, or sometimes this is also called the evidence. Then up there, we have the probability of X given that we have class 1. Let me scroll way back up. See these things that I had drawn here? These were the probabilities of X given that we know that this is class 1 or X given class 2. These were what these pictures were about. I'm going back down. This would be the class density. Or in more general terms, if we don't deal with classification, but if we're just using Bayes' theorem, then this is also called the likelihood. This is getting small now, sorry. Class density or likelihood. And on the left-hand side, we have the posterior for short, or the posterior probability. So in our case here, we have some observation X, And we're now asking, given this observation, and given our, we have this prior estimate. So if I'm not looking at the observation, you just tell me, I have an observation, tell me what class it's likely from. Well, if you don't tell me what the observation is, all that I have is the prior probability. So if the chances are 70-30, going back to this skin tumor example, yeah. So if you just, without showing me the image, ask me, there's an image, will there likely be a tumor on it? Then the answer is probably no, because most images don't show tumors. Yeah? So this would be the prior probability. But now we've updated this because now we have made this. You have revealed this measurement, and then we can combine this knowledge from, assuming this was class 1, what's the probability of making that observation X? We can combine it with the prior probability, and we normalize by the density, to get our posterior estimate. What's the probability of having class 1 at that location in feature space? All right, and now here is a fairly elaborate toy example, which just shows all these terms. I have a two-dimensional feature space. What we normally get are just the observations. Yeah? So here I have a blue class and I have a red class. But here these observations have been sampled from some true underlying distribution. And shown here is the true class density of what's the probability of getting a particular combination of observations, x1 and x2, given that in reality the sample comes from class 1, or given that in reality it comes from class 2. So these are the class densities for the first class and for the second class. Now in the numerator here of Bayes' theorem, I multiply them with the prior probabilities. So here I've multiplied them with the prior probability, and multiplying them with the constant means the shape of the object does not change at all. The only change you see is here in the scaling. So I think the probabilities were 70% for this class and 50% for that class. All right. Then we can add these class densities up in the numerator. I can add this and that, multiply them with the respective priors. So I can add up this one and that one to get the overall density. So that's the probability of finding a particular point in feature space, no matter what its true class is. And now we have all the ingredients here, so we can plug this into Bayes' theorem and compute the left-hand side, compute the posterior probability. And that's what's shown here on the right-hand side. Those are the posterior probabilities for class 1, given some location x, or for some class 2, given a location x. So in other words, if I'm somewhere here, then I have a large posterior probability for class 2. It's practically 1. So it means I'm going to predict the blue class, whereas if I'm somewhere here, the posterior probability for class 2 is very low, but the posterior probability for class 1 is very high. So I'm going to predict the red class. And now, well, we want to get out a classifier. So we are going to find the threshold here. Yeah? So remember the rule. The rule that we derived was that we always try to predict the class which has the largest posterior probability at that point in feature space. So wherever, here class 1 has a larger posterior probability than class 2, I'm going to predict class 1, and vice versa. Now my rule has a phase transition, or well, the set of points where I change from predicting this class to predicting that class, and that's the set of points where the two posterior probabilities are equally large. So I'm looking for the set of points where the posterior probability is 1/2, 1/2. And the set of points for which the probability, both posterior probabilities are 1/2, is shown here in green. So this green thing, that's your perfect decision boundary. This is the best classifier there is for this data set and for the 0-1 loss function. Not for this data set, for this distribution. So this is the very best thing there is. And well, you see that the base risk is not 0 because I have blue observations outside my contour and I have red observations inside my contour. So even this very best possible classifier is not perfect, but that's as good as it gets. No classifier in expectation is going to be better than the one you see here. And now in reality, of course, well, we never have the true densities. We don't have the thing on the right-hand side. We only have this. So what we then do in so-called generative classification methods is that given the sample data, we try and estimate, on the one hand, the prior probability. So we just ask how many red points are there and how many blue points are there. This will give us a prior probability for class 1 versus class 2. And then secondly, we try and estimate these class densities. So I can do, for example, a kernel density estimate on the red points to get something similar to that. And I can do a kernel density estimate on the blue points to get something similar to that. But it's not going to be perfect, of course, because you've seen how your kernel density estimates from finite sample sizes, how they exhibit variance, how they will not be perfect. Good. Do you have questions for this? Can a non-deterministic classifier be better? Yeah. Well, even for the non-deterministic classifier, we could take another expectation and say, over all the outputs that it could possibly predict, what is it going to do, and that will again be a deterministic classifier. Yeah? So on single training sets, yes. You can always, classifier can also be somebody reading the palm or somebody throwing dice. And it's possible that, on a finite training set, this oracle is going to be perfect. It's just very unlikely. So here we look on, we always study what's happening in expectation across very many predictions. Let me make a big picture. If you could sort of passively understand these lines here, how we go from one equality sign to the next, that would be really nice. But you will survive, this class, and you can be successful in machine learning even without following these equations. However, this picture is something that you should really understand, and this is a good point to ask questions. Why do we set the threshold at 1/2? Because for the two posterior probabilities for two classes, they sum up to 1. Yeah? And the rule that we derived here before the break was that we should always take the bigger one. And the bigger quantity out of 2, which sum up to 1, means that the threshold must be at 1/2. If and your question is interesting because if we had chosen different costs, if one mistake here is 100 times worse than the other mistake, then the best threshold will not be at 1/2. Yeah? But then you will be much more, you're looking to make 100 errors of one kind to avoid a single error of the other kind. And then you will push your threshold accordingly. And that means, if it's very important to not miss any of the blue points for whatever reason, you must correctly predict. If it is a blue point, you should really predict blue. If it's red and you predict blue, it's not so bad. That means we're going to threshold here, we had the green line. We're going to put our threshold much further out. We're going to put it here rather than where you saw it there. We're becoming more sensitive than to the blue class. More questions? Is it completely unclear or is it completely clear? That's not a clear question that I asked. Who would like me to go through this one more time? Okay. And can you maybe ask a question to help me go through it? Yes.
Can you explain again what this posterior actually means and why it's called posterior?
Okay. So why is it called posterior was one question, and then you asked about the pi or the pi. Okay. Here, this is just, I've mixed notation, excuse me. Pi 1 means the probability of, the prior probability of class 1. Okay, very same thing. Thanks for clarifying that. So pi 2 is probability of 2. Good. So your question had two parts. One part was, why is it called posterior? And this is just whenever we apply Bayes' theorem, we always start with some prior assumption, or we start with a distribution that describes our prior knowledge. Yeah, so I don't really see the sky now. If you ask me, is it raining now? Then my prior would be that in Heidelberg, 4 days out of 5 it's not raining. So the prior would be that it's not raining. Then I update this with the likelihood. If it did rain, would I be able to see it from this strange, double pane window or the reflection in the next building? And this likelihood of actually me seeing the rain, if there is rain, is not going to be 1. It's going to be smaller. And when I combine the two, my prior knowledge plus the update with whatever observation I can make, and then I obtain the posterior. So whenever we apply Bayes' theorem, we update our prior knowledge with some observation and we get a posterior. This is why it's called posterior. That was one half of your question. The other half was, what is the meaning of it? The meaning of this is, the entire process here is a probabilistic one. Yeah? So at a given point in feature space, like at this point in feature space, if I get a sample here, I cannot never say for sure it's going to be red or it's going to be blue, because there is some overlap between the classes. We have this class, we have that class, and they simply have spatial overlap. So in this region here, I can never say with certainty it's going to be blue or red. But I can say with what probability is it going to be blue or red. And that's the posterior probability. And so I can ask for this measurement in this point in feature space, what's the posterior probability that it will be a red sample? Well, then I read in this diagram, whatever is this value here, is pretty close to 1. So that's here in this context what posterior means. Yes?
And I'm calculating the posterior probability because if I have an X, or I know that, basically if I have an X, I would take the highest posterior probability and assign that class to the X.
Yes, exactly.
Okay, and if it's just 2,
Yes, precisely. Yeah, so I always, if the loss function is the 0, 1 loss, I always predict the class which locally has the highest, the class which, if multiplied with a prior, has locally the highest density. Yeah, that's the one I'm going to predict. And in the end of the day, that's a very intuitive result, right? What class are you going to predict? Well, the one which has the highest density there. So it's actually a very intuitive rule, but we have proven mathematically that this is actually the optimal rule. Good. Now, let me make another comment. In machine learning, sometimes one makes a distinction between generative and discriminative classifiers. And generative classifiers estimate the terms on the right-hand side. So generative classifiers estimate the prior and the class density and so on. These are called generative. And then there are discriminative classifiers. And they directly estimate the posterior probability. Without this detour of estimating the class density. Now this distinction, there is a certain gray area between the two, but it's a popular distinction. Let's say k nearest neighbors, generative or discriminative? Okay, we do a voting. Who thinks k nearest neighbors is generative? Who thinks it estimates the class densities? Who thinks it's discriminative? Yeah, great. Very good. Yeah, so K and N or random forest are discriminative classifiers. Today, for a change, let's look at a generative classifier. Let's try and estimate the density, the class densities directly. One way to do it would be using a kernel density estimate for each class. However, typically in machine learning, I have too few points and too many dimensions, so such a kernel density estimate is not going to be very reliable. So instead, what people do is to use a really simple model for each class, namely to approximate each class simply with single Gaussian distribution. And this is a method called quadratic discriminant analysis, which I want to talk about next. And for that, we need this multivariate Gaussian. And so let's talk about that for a moment. The multivariate Gaussian or multivariate normal has two parameters. One is its mean, where is it located, and the other one is its covariance. And for those who haven't seen it before, I want to give the covariance of a random vector. So this is now a random vector with p entries. And the covariance of this random vector is the expectation of x minus e of x transpose times x minus e of x. Okay, so what we have on the left-hand side, oh, sorry, I'm wrong with the transpose here. The transpose is on the second term. Excuse me. So the left-hand side is p times 1. The right-hand side is 1 times p. And so overall, this entire thing is going to be p by p. And you can multiply it out, and then you find that you could rewrite it as x transpose minus the expectation of x times the expectation of x transpose. And I'm omitting the intermediate lines here. If you want to, it's really just one line or so. What you need to remember here is that if you take the expectation with respect to some random variable and the expectation with respect to the same random variable of some random variable, then this is the same as just taking the expectation. Why? Because the expectation of x, this thing here is a constant. It's no longer a random variable. And the expectation of a constant is the constant itself. Good. Then the covariance of some matrix A times x. Now, this here is some matrix. So this is an affine transformation here. And this is again the random variable. Is A times the covariance of x times A transpose. And if you want to estimate it empirically, then you can use 1 over n minus 1 times S, where S is the scatter matrix that we've seen, I think, in the first week when we were discussing PCA. So this is X times the centering matrix. Good, and why n minus 1 and not n? That depends if you know the mean. If you have to estimate the mean, then you would use n minus 1 to get an unbiased estimate. Good, so this is the definition of covariance. So it's a p by p vector. And it has in its diagonal the variance, so the spread along the different dimensions, and it has in the off diagonal the covariance, which tells us how much linear association is between random variables along different dimensions. And I have a few pictures here. So these are some isocontours of a multivariate Gaussian. And yes, the Gaussian itself, I still have to give you the formula. But it already gives you a feeling for these covariance matrices. So here we would have a variance of 1 along this axis and along that axis. And we have some negative entries here, so we have some negative correlation. Here, the negative correlation has become stronger. If it were infinitely strong, so then I would have a minus 1 here and a minus 1 there, then the points would be, or my distribution would be concentrated along this diagonal line here. Here I have some positive correlation. You see I have a positive number. And now between the two axes, I have a positive correlation. So if I observe a large value on this axis, then I'm also more likely to observe a large value on that axis. And for negative correlation, well, it's the other way around. Yes?
The equation next to empirical estimate implicates that C transpose is the one matrix, right? And then C would also be...
No, it's just that it's this idempotent thing. Yeah, so C times C transpose is C. It's not the identity matrix. You remember it's a centering matrix, and if I center my data once, if I center it again, nothing else is going to happen. It's already centered. Okay. If you go back to the definition, so C was identity matrix minus 1 over n, and then this was a column vector of ones, and this was a row vector of ones. If you just multiply it with itself, you will see that it results in itself. It's a projection operator. And there was somebody else? Yeah?
To me, it was the same question.
Oh, good. All right. Good. Now, well, we come actually to the normal distribution. The multivariate Gaussian, and it's so important that the statisticians, they don't call it Gaussian, they call it normal. The multivariate normal or just the normal distribution has some normalization constant which depends on the dimensionality and depends on the covariance matrix. And I always forget it. But what we see is here that with growing dimension, we get a smaller and smaller normalization constant. And then this is the determinant of the covariance to the power of 1/2. Yeah? So the bigger our spread, the smaller. Excuse me. The bigger the spread, and the smaller this normalization concept. So I'm happy if you just remember that there is some constant depending on p and sigma. Okay. But what you must remember is the following: that it's x minus mu transpose times sigma to the -1 times x minus mu. Yeah, where mu is the mean, so where is our Gaussian centered, and this is the inverse covariance matrix, which is also called the precision matrix. Whence this name? Well, if I have a big spread, then I have, in a sense, little precision in the spatial localization, okay, and vice versa. And of course, if my covariance matrix becomes big, then by taking this inverse operation, the precision becomes small, and the other way around. Good. What we need to know is that and by the way, here, these are of course all vectors. Yeah. So x is a vector here. What we need to know is that the marginal of a normal distribution is also normal, and the conditional of the normal is also a normal distribution. Yeah, so for example here, x could have two components, and if I now fix one of these components, so let's say I'm now conditioning on here x1 being minus 0.5, for example, then if I now look at the conditional distribution along this line, I will again find a Gaussian. Yes?
Which norm do we use with regard to the covariance matrix?
That's a determinant.
Okay.
Good. All right. What is not true is that if we have normal marginals, that does not imply that we have a Gaussian distribution. So normal marginals normal, no, this is wrong. In this picture is an illustration here. Here I have some joint distribution. It's actually the sum of two, the sum of a highly correlated and highly anti-correlated Gaussian. The marginals are normal, but the joint distribution, of course, is not a Gaussian. Good. And now this is what we're going to use in QDA. Yeah? So in quadratic discriminant analysis. So what we do in quadratic discriminant analysis is that we approximate, let's say we're given this sample here, and now we approximate the red class with a single Gaussian. To that end, we first estimate the center of mass, and then we estimate the covariance matrix, like you've just seen, yeah, in terms of the scatter matrix. And so if I approximate this red, this training data with a Gaussian, then this is what I find. Similarly, I can approximate the blue class with a Gaussian, and this is what I find. And then I can plug everything into Bayes' theorem, and I find this decision boundary, which is not bad, but it's of course not the Bayes classifier. This green decision threshold is not the one that we saw before. It's not the best possible one. So QDA stands for quadratic discriminant analysis. And what we do in QDA is we approximate each class in the training data by a single Gaussian, so one per class. To approximate by a single Gaussian, well, we estimate the mean, so we just compute the center of mass, and we estimate the covariance matrix using the formula that you've just seen. And then we plug into Bayes' theorem, and that's it. Plug into Bayes' theorem and compute the posterior probability. Okay, actually I also need to estimate the prior, but estimating the prior is really simple. I just count out of all points how many are blue and how many are red. Yeah? I think you two had a question? No? Now, astute observer notices that in this decision contour here, it looks like an ellipsis. And why is that? Let's look at the math. Can I scroll up? Down? So, let's look at the shape of the decision boundary. To find our decision boundary, we equate the probabilities for class 1 given x with the probability of class 2 given x, if it's just two classes. Now, okay, we can say that following Bayes' theorem, yeah, I would do x given 1 times p of 1 divided by p of x equals probability of x given 2 times p of 2 divided by p of x. The p of x is the same on either side, so this cancels. And how about the rest? I will have a normalization constant 1 times e to the minus 1 over 2 x minus mu 1 times transpose times sigma minus 1 x minus mu 1 times p of 1. And on the other side, I have normalization constant times p of 2. All right, and if I now take logarithms on either side, then I find the following. I find that I get ln C1 times P of 1 divided by C of 2 times P of 2 minus 1/2 minus 1/2 or plus 1/2 equals 0. And here I was just a bit lazy. X minus mu 2 transpose x minus mu 2. And we have a sigma 1 and a sigma 2. Sorry, we have different covariance matrices in general, okay? Sigma 1 and sigma 2. There and there. All right, and what we find now is that altogether, this is just some constant. So this is a scalar. And this other thing, whatever it is, we can multiply out and so on and so on. But we find something which is quadratic in x. And if we now look for the set of solutions, so, for which x does this equality hold? What I find is that overall, I get out quadrics. And quadrics is a catch-all term for an ellipse or a hyperbola or a parabola or parallel lines, a single parallel line or two parallel lines. These are all quadrics. And so what we find is that the decision boundaries of quadratic discriminant analysis are always quadrics. Okay, so we've seen why this is a plausible shape. We got out a decision boundary which was a parabola for these particular, which was an ellipsis for these two particular Gaussians that are estimated for the one class and for the other class. Good. You've been very brave today. The theoretical part was as difficult as it gets. From now on, it's all easier. And we've seen the first generative method in which we simply approximate each class with a single Gaussian, then plug it into Bayes' theorem, then get a posterior, and we've seen the decision boundaries are quadrics. Equipped with this knowledge, enjoy your lunch. Thanks.